Alrighty, episode. Actually, I don't even know what episode we're on nowadays, but that's okay. 'Cause we're making good progress today. I'm joined by Professor Paul Rablen from Swarthmore College. Is it college or university? College,
College. Yeah.
college. In the great Northeast, Southeast Pennsylvania, where I'm from. So kind of a bias towards that area, but it's a great little town and area. I graduated I don't know, 15 minutes south of Swarthmore, not even at Widener University. So
Mhm.
definitely neighbors in that aspect. So yeah, really excited to have him on today. More of a computational chemist, so it's a little bit. I know kind of. I know the basics, but I'm looking forward to diving into that some more today. But I guess the first thing we can start with is a little bit back about yourself. I know you went to Haverford College, so I know you're probably from that relative area. But I don't know if you want to dive into a little bit of your background for the viewers to get
Yeah,
a
sure.
sense
No,
for
I
your.
actually I grew up in I was born in Massachusetts
Mm,
and grew up in Connecticut. Um, but then, as you observed, I went to Haverford uh, as an undergraduate,
yeah.
um,
Now, did
and
you
then
did you like high school? You were in the Connecticut area or Massachusetts area? Yeah.
in
Okay.
Connecticut. Yeah.
Okay.
So
In
the part of
Connecticut.
Connecticut where I grew up most of the time is the southeastern part near the Rhode Island border.
Okay.
There's a small city there called New London. I didn't live right in New London. I lived in Waterford, or actually Quaker Hills, the name of the subdivision of Waterford, which is
Mm,
just a little town outside the city itself. But
mm.
that's where I grew up, and that's where I lived from, I guess, about age 6 until I went off to college.
Yeah, it's a great area up there. I've been up to Rhode Island once, and I kind of just like that area, that vibe. It's
Mhm.
very um, mm, I like the harbor. I don't know. I like that kind
Mhm.
of
The
that
seaport, yeah.
area, the seaport. I like that kind of vibe.
Yeah.
Um, Weather can be a little bit brutal up there. Can be, but is what it is. Did you do any like skiing up there at all?
When I was a little kid, we did some.
Yeah.
The truth is that area doesn't get a whole lot of snow usually because the ocean really moderates the climate.
Oh,
Um,
interesting.
so
Okay.
so they get a lot less snow than even just an hour away further inland. There's a good deal more snow, and certainly in Vermont and New Hampshire there is.
Hmm.
But yeah, as a kid, uh, once or twice, I think I went with my mom for a somewhat more extended, a few days of a ski vacation. But certainly, what we did in the winter sometimes was just take a day trip, usually to a place called Pine Top that was in Rhode Island, as I
Okay.
recall. Um, that was, just a small little ski place.
Yeah.
And we do that, and then cross country skiing sometimes too. Although that more often when I got to be a little older, like a teenager. In part because I had a friend who lived in Bennington, Vermont,
Hmm.
and we went up to visit him sometimes, and that was a good place to do cross country skiing.
I was gonna say I think Bennington, Vermont's a very good area to go up in.
Yeah, yeah, that's
Really,
good.
winter sports in general. Um, any other like big hobbies, activities, kind of growing up?
My mom always liked to take walks, and I think that sort of rubbed off on me. And
Fair
so
enough.
that's to this day what I do as my main form of exercise. And one of the main things I like to do when I have vacation time is hiking,
Hmm.
particularly hiking in mountains if I can arrange it.
Yeah, and that's great, especially up in the Northeast, because I feel like something very underappreciated when I moved down into Houston is the definitely change in kind of the seasons. So like I
Yep,
think
yep,
um, if being outside in
yeah,
in the trees
yep.
is very you kind of don't appreciate that until you don't have it anymore.
Mm-hmm, mm-hmm, yeah.
So how were you always interested in like chemistry in the STEM fields? Was that kind of a
I was certainly always interested in STEM fields. I think that's
yeah?
fair to say.
Hmm.
Chemistry, maybe to some extent, although to a large extent, I also think it's just what I kind of uh, fell into by happenstance.
Hmm.
So I do remember, as a little kid, I was actually mostly interested in astronomy, I'd say, and to some extent physics. I always liked math. That was typically one of my favorite subjects in high school.
Yeah.
Uh, and I certainly had, lots of books about astronomy and so on and so forth. And I loved to read Isaac Asimov, who, he wrote science fiction, but he also wrote a lot of, brief science fact
Mhm.
essays that I was liked a lot. Um, but I do also remember that I was kind of fascinated by the periodic table at a young age. Um, so I used to look it up in our big encyclopedia. And I mean, I think what particularly was interesting to me is that there's this enormous variety of stuff in the world and the universe, and yet it's only made up of a very limited, finite set of different building blocks.
Yeah,
But anyway, when I first went to college, I was actually I didn't really know what I wanted to major in, but what
sure.
I put down and what I started out majoring in was actually physics.
Mm.
Um, and it was only later that I switched to chemistry.
I was gonna say, I mean, we'll talk about this a little bit later, but computational chemistry is basically it's basically bordering physics now.
Yes, that's right, and I and so I think it's not a coincidence that that's where I've ended up.
Yeah,
You're absolutely right.
that's really really cool. Yeah, I think talking like when you people like talk about STEM, this is something I've talked about with other professors too. I don't know your thoughts on this, but kind of like the marketability of chemistry is very interesting. I think because when you think about astronomy and physics and mathematics, especially like astronomy and let's say astrophysics, like it's really like cool to like the abstract of like,
Yeah.
oh yeah, the stars and the galaxies, and we can um um we can prove the Big Bang because the galaxies are accelerating out and all all that kind of like really
Hmm.
abstract like stuff. I mean, physics when you start talking like 11th dimensions and micro universe, the macro universe, like it's all like super cool. But then you kind of get to chemistry, which is another I would say central science, and it's like yeah, we have plastics that are polluting the world, or in the oceans we got oil and gas, greenhouse gases. So it's all like it's almost like this negative connotations to it. Now it's not all like that, of course, but I don't know. I think the marketability of chemistry is definitely behind in that aspect. I don't know if you have any like kind of just thoughts on this and
Thoughts back. Yeah, well, I
yeah.
mean, it depends a little bit what you mean by marketability. When you said marketability, I thought you were actually going to go in a different direction, which is to say something like, yeah, the astronomy sounds all cool and nice, but you're going to have a hard time finding a job doing that.
That is
Um,
true.
right, because I think that's the thing. Some of those areas are fascinating, but there's really not much of a job market outside of academia,
Yeah,
and there's only
academia.
a limited number of academic jobs. Whereas in chemistry, there's a big, healthy market in industry for
Mm.
chemists, as well as in the government and in academia. So, um, so I guess what you're talking about. Maybe I'm marketability may not be the word I'd use to describe that. I might say that more like, I don't know, public impression or something like that.
Yeah,
And I think one of the difficulties there is all those things you're mentioning. There are environmental aspects that are problematic that we're dealing with now, but nonetheless, the reason those things became problematic in the first place is because they're so useful to society,
yeah,
right? I mean, the truth is, plastics, despite their problems, are also very useful for all sorts of things. And oil and gas, well, one needs to have an energy source, and yes, now with climate change and such, we recognize the need to move away from fossil fuels. But nonetheless, another way of looking at it is all the advances around us, all the advantages that came with the Industrial Revolution and what came subsequently, wouldn't have been possible without an energy source. And
yeah.
up until fairly recently, fossil fuels that's what was available.
Hmm.
I mean, yeah, you can do a certain amount with water wheels and such, but for more heavy duty industrial processes, um, you needed something more. And now we have new options, right? Solar
Yeah,
energy has developed a lot. Actually, you can do a fair amount with hydroelectric in the right environments.
yeah.
Um, and wind power and nuclear, actually, I think is also a good option. It's a more controversial one. Um, But anyway, that's all to say that I think there's a tendency uh, on the part of the public sometimes to focus on some of the negative consequences that come with technological development and the role of chemistry in that.
Yeah.
But I think it's important to remember that without technology, including what chemistry has to provide, our lives would be a whole lot different, and I think not generally for the better.
Yeah.
I think we live a whole lot better than people did, say, in the 1500s and the 1600s and even the 1700s before all this technology came along.
Yeah, certainly like modern medicine, things like that. There definitely has been I would argue, a net good for sure.
Yeah, or even just sanitation, right? I mean, we take
Yep.
for granted that we can turn on the water and have water that it's safe to drink.
Yeah.
And what allows that? That's chemistry, right? That's water treatment, including chlorination and such. That's why it's safe for us to drink the water that comes out of the tap. That wasn't something that people could assume, like, 100 years ago, or at least 200 years ago.
Yeah, there's certainly a lot of good to take in. People got to remember the good, and also too, I guess when people are inventing all these things, they couldn't have predicted how like the issues that would arise, right? And that's kind of what
In some
happens.
cases, yeah. Yeah. I mean,
For
there are
most
other
times,
cases where, I mean, that's a fair point. There are other cases where perhaps people and society could have done a little better job of anticipating what might be problems.
yeah,
And I think we're getting better at that.
yeah,
But,
and
but
it
yeah, you
and
can't predict everything.
and it, in especially like in academia, like people are trying to tackle these problems. It's like they really are. Like, academia is trying to tackle a lot of these problems. So that's definitely one of the silver linings, and also science in general can be a huge let's say gray area, can be. But I guess so you grew up in, I guess what I'm curious about is you grew up in the Connecticut area, but you went to
Yep.
college at Haverford. So it seems
hmm
like Haverford's kind of like a relatively small college. So I'm kind of curious to how you kind of ended up there.
So I guess part of it is that my dad had gone to a small college. He went to
Okay.
DePaul University, actually out in Indiana,
Mm,
and and so I guess that was somewhat in my background. And the high school where I went was actually a small high school. In fact, where I grew up in Connecticut was only about a mile from the campus of Connecticut College,
okay.
and the high school where I went is sort of on the edge of that campus. Uh, and it was a small high school. There were 31 students in my graduating class from high school.
Oh wow.
And so I think the idea of small schools was something that I'd grown up with.
Yeah.
So that's part of the answer. And then part of the answer, too, is that um, my dad's wife had mentioned to me at one point that Haverford was a college that she knew somebody who went to and had liked it very much. And that's really how I first started to look at it. And,
Hmm.
I used what was the guides that they had at the time, which were much more limited than the ones that are available now. But Haverford looked like a good fit. So it was among the schools that I applied to back then. I applied to 6 schools, which back then was considered a fairly large number of schools. Now students apply to 10, 20 schools. It's kind of gotten a bit crazy.
Whatever you can afford to apply to, right? Whatever the application fee costs, I guess. Right.
To some extent, yeah. So anyway, yeah, but in some ways it was again a little bit of happenstance. I did apply to big places as well as small places, and I guess part of my decision in the end was to go to a small place, which it felt more comfortable to me, especially having come from pretty much a small town background and a small high school. The
Yeah.
idea of going to a great big university was a bit intimidating.
I know a couple people up in Connecticut, and I feel like the fate is always UConn, which is a great school. But
Yeah,
like,
and that's I also applied. That was sort of my safety school. Was the
right,
University of Connecticut.
right. I Yeah, it's I think what are the other big schools in Connecticut? I don't. The
Well, there's
UConn.
Yale, right?
Oh,
There's
that's right.
Yale,
Yeah,
right?
of course, of course.
There's, as you said, the University of Connecticut.
Yeah,
Those are probably the two best known. There's also University of Bridgeport, but that's sort of more a school that serves the local area.
yeah.
Um, there's Wesleyan University in Middletown, Connecticut.
Wesleyan.
Uh,
Yeah, that's another one.
yeah, which
Okay.
is it's not as big as certainly the University of Connecticut or Yale, but it's well known.
Yeah.
And then
So
there's the Connecticut the State University of Connecticut system, which has a bunch of campuses.
mhm. Now, so moving down to Haverford, then you said you like didn't. I guess you originally applied for physics. So like, I guess
Mhm.
were you? Is their physics program kind of good there, or was it kind of more so you kind of go get away from home, get away
Yeah,
from experience?
I was choosing a college as a college. I wasn't choosing a particular program.
I mean, you
Um,
didn't think about these
but
things at 18. You didn't think about what you
no,
want to do with your life.
no, I didn't. um,
But
and so anyway, yeah, no, I started out as a physics major. That's right.
mhm.
And I did
And
that for the first 2 years, really. I actually
okay,
even I declared a physics major, but then shortly after declaring it, I actually switched to a chemistry major.
fair enough. And then so doing your undergrad, what did you do like undergraduate research? And then
I
how?
did. I did some only during my senior year. So
Yeah.
the summer before my senior year, and then my senior year, and then the summer after my senior year. Actually, I did undergraduate research with a synthetic organic chemist.
Okay.
Um, and it was a pretty, undergraduate research back then, I would say, was a less big deal and a less common thing than it is today. It
Mm,
certainly tended to be somewhat smaller scale than, for instance, I'd say the research that goes on here at Swarthmore or at Haverford today. So
sure.
anyway, what I worked on was basically a potential lab exercise for undergraduates, sort of a synthesis and stereochemistry project. And it was eventually published in the Journal of Chemical Education. That's what I did as undergraduate research.
And you realize you never want to do synthetic chemistry again. You
No,
turn your
actually, that's not what I realized. I initially thought that's what I thought I originally would do in graduate school. Although
Okay.
after getting to graduate school, I fairly quickly realized that's not what I was going to do. Actually, I just realized what I told you is not quite correct about undergraduate research.
Sure.
So the summer before my senior year, I did, and then the senior year, I did what I was just telling you. But then the summer after my senior year, I actually did some research for a different professor or with a different professor that was NMR work.
Okay.
And that work, it turns out, I ended up actually using to some degree when I was in graduate school and also when I began here at Swarthmore.
What were you working
So,
on like as a because they
so,
can get
so
pretty advanced those NMR
yeah. So
techniques.
the NMR that I worked on, it's long enough ago that I don't remember the specifics anymore about what the system was we were looking at.
Fair
But
enough.
the technique was um, the technique was one for measuring the rate of certain processes by NMR on time scales that are, probably too fast that for you to be able to monitor it just by taking successive spectra,
Okay.
but that are too slow to be measured very accurately by the traditional line shape analysis method.
Okay.
There's the classic example in some ways, this is the one that I actually worked on later in graduate school, is to consider the rotation around the CN bond of an amide.
Hmm.
Right? So that bond has partial double bond character, and
Yeah.
so the barrier to rotation is on the order of 15 to 20 kilocalories per mole, depending on the particular amide. And that means that the rate of that rotation, again, depending on the amide and depending exactly on the temperature, can be anywhere from a few hundred times a second down to only once every few seconds.
Mhm.
So at the higher end of that rate, you can use line shape analysis. So, for instance, as you raise the temperature, lower temperatures, you see two separate peaks in the NMR for, say, the two methyls of NN-dimethylformamide or acetamide, and then as the temperature goes up, and the time scale, of an NMR measurement is in the order of a second. And so when the rate of exchange is much less than once per second, you just see the separate peaks. But then if the rate of exchange is much faster than once per second, you just see one averaged peak.
Yeah.
And between the two, as you might imagine, right? You may already know everything I'm just telling you, but just in
Oh man,
case and just in case people in the audience
yeah.
don't.
This is
Um,
yeah. Most of the time, it's
uh,
for people in the audience. Yeah.
so
And well,
then
and for me, but
the lines gradually, the individual lines, as the process of exchange becomes faster, the lines broaden, and
mhm.
then they eventually merge into a single first broad line and then eventually a single narrow line. And by analyzing the line shape mathematically, you can extract the rate of exchange. But that only works if it's relatively fast. As it gets, I mean, not super fast, but relatively fast. As it gets slower, the line shape is dominated just by the natural line width and not by this exchange process. And so then there's a different technique, which goes by various names, but the one I like is selective inversion recovery. And basically you use a pulse sequence to invert in the NMR one of the two peaks, and then you wait a variable amount of time, and during that variable amount of time, since these methyl groups are exchanging positions, basically these peaks exchange intensity. This one gets lower, this one gets less negative. And then in addition, there's just a natural decay going on. And so both of those processes have to be modeled in these peak heights, or peak intervals, really. But you choose different intervals of time, and from the behavior of these intensities after different waiting times, you can extract out the rate constant of exchange, and that works for considerably slower rates of exchange. So that was the technique I was using in the work I was doing that second summer, although, as I said, I actually no longer recall what the particular system was that we were looking at or why it was interesting.
That's okay. That's still really cool. That's really cool. Well, technique, really, because I mean, I was watching a few lectures on like NMR, because I'm like organometallic chemist. I kind of use your basic, fluorine, phosphorus, protons.
Yep.
But all those 2D techniques, all those like, dynamic dissolution, nuclear polarization. I mean, all those like fancy techniques I'll probably never use. So it's just really cool to like see what is available to you, because you really can do a lot with it.
Oh, it's amazing how much you can do with NMR.
Mm-hmm. Really very, very awesome technique. So you're doing some undergraduate research. I'm curious, in general, how was your time at Haverford? I mean, did you overall enjoy your time there?
Overall, I enjoyed it. Yeah. No, I mean, I think socially, particularly in the earlier years, I think socially I enjoyed it quite a bit. That is, being, again, in a smaller environment, that worked well for me.
It's a nice campus.
I'm sorry?
It's a nice campus like that.
Yeah, it's very pretty. I think Swarthmore's is even prettier, honestly. But yeah, Haverford's is a very nice campus. Mm-hmm. And certainly, I had excellent professors and enjoyed the fact that, I could get to know them and actually work closely with them, as opposed to, just being only in big lectures. Although even, the organic chemistry classes I had were actually fairly large lectures, and it depends what you mean by large, but they were very good.
Probably large relative to the amount of students you have.
Large compared to other classes. So
I'm
trying to remember. I think probably my organic chemistry classes were, maybe 60 students, something like that.
Yeah.
But, most classes were 20 or fewer, I would say.
That's how mine were. Because at least for organic, because there wasn't like there's mostly chemical engineers and some chemistry, but most of the people in the class were like doctors of physics, or like going to be PT students, basically.
Right. Yeah.
So no, I hear that.
Yeah. Which, by the way, is why I was taking organic chemistry. Remember, I told you I started as a physics major.
Yeah.
So the reason I was taking organic chemistry in the first place is because I didn't really know what I wanted to do after college, and medicine seemed something that might be a good possibility. And so I was covering pre-med requirements. And actually at one time that really was what I thought was my most likely career track. And so that's why I was taking organic chemistry. And in some sense, the reason, I changed my major from physics to chemistry was not part of a long-term career plan. It's just, I thought, well, I'm going to go to medical school after this. And so it doesn't really matter what I major in. And I was thinking, well, I'm enjoying my chemistry classes more than my physics classes. So why don't I major in chemistry instead of physics? And that was really the extent of the thinking.
So then going into graduate school, then was that how did that decision come about
happen?
Then?
Yeah. So I said, so maybe the best way to describe my frame of mind would be like this. So it certainly was largely a financial decision.
Sure.
So the difference is medical school costs a lot to go to. Graduate school, you get paid to go.
Yeah.
And so I think the way I would say it is this. If the situation had been you got paid a stipend to do either one, I'm pretty sure I would have gone to medical school.
Mm.
If the situation was that you did not get paid a stipend to do either one, that you had to pay your own way, then my guess is maybe I would have gone to medical school, or maybe I simply would have done neither, at least for the time being. I would have gone out and gotten a job.
Mm.
Given that going to graduate school, you got paid a stipend, and that to go to medical school is going to be expensive, I decided to go to graduate school. Now, it wasn't entirely, that is, if I had felt in my heart that, medical school is definitely 100% what I want to do, I think I would have, just bitten the bullet, so to speak, and gone ahead and done it anyway.
Yeah.
But I wasn't that positive.
Yeah.
I had some doubts. And I suppose in some ways what I had in the back of my mind is, given that medical school is so expensive and such, I can't afford to go and then decide I don't like it.
Yeah.
Whereas
Yeah.
I felt, I can afford to go to graduate school and decide I don't like it because, I'm paying my own way. I'm basically earning a living even as I go. Although in some sense, I think I underestimated the degree to which once you embark on a path like that, you're kind of on it. It's not so easy to switch paths or do something different. But anyway, that's that's more or less how I decided to go to graduate school instead. And I guess the other thing I say is that part of my interest in medicine was thinking that I'd like to work with people, but I also like teaching. I was a TA already as an undergraduate on some occasions, and I really enjoyed that a lot. And so the other part of it was deciding that, I like this idea of working with people, but I'd like to work with people as, sort of as thinking entities, as personalities, not as physical entities, as bodies.
Yeah.
And so I sort of started to realize maybe I'd actually enjoy teaching as a way of interacting with people in a professional context more than being a physician.
Yeah.
So, and anyway,
Yeah.
and if I'd become a physician, I actually was considering psychiatry as the field I might go into, which is interesting because that also involves working with people at a more mental, intellectual level rather than a physical level.
I mean, it's
Both my parents, by the way, were in the mental health field. Anyway, yeah.
Yeah, it must be pretty crazy to like go back and think that you didn't at what point did you envision becoming a professor, right? It's just like
Right. So that
it's
when
like
I decided to go to graduate school, that was explicitly the idea.
okay.
That is, when I chose to go to graduate schools, it was in part, as I said, because I decided I could afford to do that, even if I wasn't sure, because I was earning my own way, and because I liked working with people as a teacher. But if I were to continue on that track, my goal was explicitly to become a faculty member, and especially to become a faculty member at a place kind of like Haverford. That is an
Yeah,
undergraduate school where there was a more of an emphasis on teaching, and a bigger part of the job was teaching as opposed to research.
I'm gonna circle around back to that later because I think I would love to have a primarily undergraduate institution role. I think that'd be super fun where you can kind of do casual research with undergraduates. The pressure to publish is not like obviously not like a tier. It's not like tier
It's not
one.
like it is at a research university. No,
You're right.
absolutely not. It's more than it used to be.
And that's
That is, when I was an undergraduate, at least at Haverford, I think that the pressure, it also varies from department to department, but I think that the extent of publishing by the faculty I had when I was an undergraduate was quite minimal. And I don't think they were really under any expectation of writing grant proposals. Um, and the research, as I said, was really quite small scale, and was really rather explicitly with the idea of giving students some sort of meaningful experience, but it didn't in a way have to accomplish that much. And I think
yeah.
that has changed over time, and there is a much greater expectation now than there was 30 years ago that the research one does at a place like Haverford or Swarthmore is really competitive with the research at big research universities. Maybe not on the same scale, certainly, in fact, certainly not on the same scale, but still sort of important and significant in a way that I think was perhaps not expected 30 years ago.
Yeah, I mean, especially because grants. I know my PI, like, grants are pretty hard to get nowadays, and
Oh yeah,
so
they're getting harder and harder to get, and there's more and more. Maybe I shouldn't say more and more, but there certainly is pressure and expectation of getting some grants at schools like Haverford and
yeah,
Swarthmore and Bryn Mawr and Pomona and so on and so forth, in a way that, again, there wasn't. I don't think there was 30 years ago. Certainly, I didn't get the impression there was at Haverford.
yeah. And I guess you'd be a good person to ask about this because I mean you are at one of these types of universities. Um, is this necessarily a bad thing? Because I mean, uh, or maybe I don't really know because at least when I did undergraduate research, like I wasn't expected to, like, my PI, like I wasn't expected to publish. I was just kind of doing it because I was interested in it fundamentally, right? That's what it always came back to. I was just fundamentally interested in it. So I wasn't expected to publish. My PI, I guess, my PI was already the associate dean, so he wasn't like
Didn't have
he
that
had to
much time. Yeah.
it's like he's not expected to like publish. He's already had a few publications, but obviously that's not the same for a lot of faculty. So I guess one question is like, where does these expectations come from? Like, it must have come from the very top and like trickled down. Like,
Yeah, that's actually an interesting question.
because I'm not
I think a
sure.
lot of it honestly comes from the faculty themselves.
Mm,
So, for instance, I mean, in order to get tenure, that has to be approved by a committee that
yeah,
consists of faculty members. You get letters from faculty members in your own department as well as some outside departments at the same school and also from other schools. And then there's a committee of faculty and administrators that judges everything.
mm,
But it's just part of the ethos. I'm not sure how much it comes from the top. I'm almost inclined to say it comes more from the faculty themselves. And I think that one of the things that has changed is that in the last few decades, I think the faculty hired at places like this are simply more research ambitious than the faculty who were hired at these institutions in an earlier era.
I see.
I
Yeah.
don't know exactly why that's true. Um,
I guess what I meant by it from the top, I meant like, let's say I mean, people who graduate from research institutions, they come take positions at the primary undergraduate institution. Like, naturally, they're going to have more, I guess, research ambitions, like you said, and then
mhm.
over time, it just naturally progresses into the expectations grow and grow.
Yeah,
So
yeah,
it's just,
perhaps that's a good way to look at it.
I
I
guess,
think also, there was a period starting maybe in the 50s and 60s when research grant money was quite readily available, and I think research expectations across the spectrum kind of
yeah,
grew at that time, and as you said, then sort of trickled down from the research universities where that began down to the smaller institutions.
yeah,
Um, and so, I mean, there's always been an expectation of research, but I think what's changed in a way is the scale and competitiveness of the
yeah.
expectations.
And people that are listening, take this with a grain of salt. What I'm about to say, I'm a second year graduate student, but I'd like to hear kind of your thoughts on this. Is like, the it seems to me in my 2 years of doing this.
Hmm.
Remember, it seems like it's always it's always about like the framing, where like it seems like where things are going nowadays. If it's not like tackling a sustainability polymer question,
Yeah,
or if it's not tackling like medicine,
yeah,
well, if we don't do this or that for big pharma,
yeah,
you're not really going to get funding, and
yeah.
that's generally the at least what I've
Yes.
seen.
No, I think you're right, and that is a change from some decades ago. When I was a graduate student, that was much less necessary. There was much more room for doing things, just arguing, well, this is sort of the next logical thing to study in this area that's interesting.
Yeah.
where we don't know what the use of it will be. Um, I mean, you always, I think, had to argue a little bit about why it would be, certainly why it's interesting. You'd have to
Right.
argue, and maybe a little bit why it's useful. But like you said, I think there's much more of an expectation now with the grants that you have to really tie it to, fairly explicitly to something that is potentially a practical application.
Yeah.
Um,
It seems like in general that it's almost like we're losing focus on like the fundamental chemistry versus like, I mean,
mhm,
we're talking like, large scale applications rather than just like
mhm.
just fundamentally understanding something at the
Yeah,
molecular atomic level.
yeah. No, I think you're right. That's absolutely true.
Do you think that that perspective can change, or I don't know? It's hard to say right now. Doesn't seem like it's
Yeah,
going to
it,
change
it, it
anytime
is hard to
soon.
say. I don't know. It depends. I think there's concerns about you know the budget deficit and so on and so forth at the national level, and so I
Yeah.
think where it comes from ultimately is politically. There's a lot of pressure uh, on the agencies like NSF and NIH and so on and so forth to justify all the money that they're investing in
Mm,
research, and that's where this comes from.
yeah, and that's tough.
Um,
I
and
don't.
that pressure wasn't there in the same way 30 years ago. To be fair, the scale of funding 30 or 40 years ago was quite a bit smaller. The research enterprise has really grown
Yeah.
in this country, and so it's at some level you can't blame the public, I think, for saying, "Hey, there's actually a lot of money being invested in this. Explain to us, show us why it's valuable." Um, but on the other hand, perhaps more could be done at kind of an intermediate level to argue that, okay, but a significant amount of research funding should be for things that are just interesting, because often what turns out to be most useful in the end is not research that was guided by a desire to do something useful. It was research
Yeah.
guided by a desire to just figure out how something works. I also
Yeah.
think it may be true that as a discipline becomes more mature, there's less that's really fundamentally not understood. And it may be that 50 years ago there was more in chemistry that was just pretty basic, that wasn't well understood yet. At least in organic chemistry, I'd say this probably is true. And today, the general principles are better understood, and so perhaps
Right.
there's less that's really important to do in terms of basic understanding. Now, interfacial areas, that's in materials science and so on and so forth, interface with biology. Yeah, I think there's still a lot of areas that are not so thoroughly understood, where really basic research is probably still very valuable.
Hmm.
But I think maybe there is something to the argument that in some of the core areas of chemistry, the principles are pretty well worked out, and maybe things that are more directly tied to applications are where it makes sense to put resources.
Yeah. It seems like. I mean, correct me if I'm wrong here. It seems like a lot of the funding's also like. Are they approved by people who like aren't necessarily chemists? Like, is that where the? I don't know how true that is.
No, no, yeah, the way the grants are reviewed is by panels of people who are
Okay.
chemists,
All right.
and usually not only chemists but chemists in areas pretty related to the areas in which the proposals are being written. Now,
Yeah.
at the very high level, there's some political influence about, say, how much money goes to chemistry as opposed to physics, or goes to the Department of Energy as opposed to NSF or NIH. I mean, of course, that is a political decision.
Hmm.
But the actual evaluation of grants is absolutely being done by experts, by
Well,
PhDs.
yeah. I mean, like you said though. I mean, that intermediate area is kind of getting back to um, more fundamental understanding. Will be. I'm curious to see how it goes over the next few years. And that's all I can really say about that. Let's see.
Yeah.
Hopefully I don't have to cross that funding bridge till I get there. I'll just leave it at that
Uh-huh.
too. I'll let my PI worry about that. um, so getting back to kind of your journey though. So because
Hmm.
I know you did a like master's at Columbia before then going to Yale, I
Yeah.
think.
Yep. That's right.
I was, um, how was your time at Columbia? What was kind
Right.
of your
Yeah.
master's thesis on, and then how did
Yeah.
you end up over at Yale?
So, uh, so I started out at Columbia, as you said. That's where I went immediately after undergrad. I was not at all happy there. I
Fair enough.
was pretty miserable there. I
Mm.
think there were several reasons for that. One of the biggest was simply that I'm not really a city person. And I had been persuaded by my undergraduate mentor that I shouldn't worry about that the only thing that was important was the science. But I think, at least for me, that was not good advice. I know that I'm sensitive. I've come to know that I'm quite sensitive to my environment. And so, and that was also at a time, that was in the late 1980s. And if you read about New York, apparently that's sort of when it was at its worst. That is, New York has gotten to be a considerably nicer place to live in the time since then. But the long and short of it is I was really miserable there, largely because of the physical environment. Although I think in addition, it was a big, as we discussed before, I'd only been at small, very personable places before.
Yeah.
And I think that it was a tough adjustment going to a big kind of impersonal university. And that was going to be tough no matter where I went.
Hmm.
But that, together with the environment that I was so uncomfortable with, I just was very unhappy there. So by the end of the first semester, I knew I wanted out. Um, and I considered at that time transferring to a different graduate school. I actually considered going out to University of California, Berkeley, which is another one of the places that I looked at initially, or to Stanford. But in the end, I decided, no, I just want out. And so
Yeah.
I actually left. And so I didn't have a master's thesis, by the way, because this was not
Okay.
a terminal master's program. What I got, so I guess the program there, I was in the Ph.D. program, but along the way, after the first year, just your coursework, you get a Master of Arts, and then a little later, you actually get a Master of Philosophy,
Hmm.
and then eventually you get the PhD. So I just got the MA because of having successfully completed, a year of coursework,
Yeah.
essentially. But that's sort of just the booby prize for if you leave. Um, and at the time, I didn't really have a plan for what to do next. And my undergraduate mentor heard about this, and he called up his buddy who was on the faculty at Yale, uh, and he knew that I liked being a TA, liked teaching, and basically say, hey, I've got this really great student who is unhappy at Columbia and is leaving, but he likes to teach. Do you have something for him? And so what landed in my lap initially was simply a job as a teaching assistant during the summer for the summer organic chemistry classes that were being taught at Yale, because they have a summer program for pre-medical students and whoever else
Sure.
wants to get a summer course in organic chemistry. And so I moved to New Haven, and because I didn't have anything else lined up at the time, and I did like teaching, and that went well, and I liked it. And as the summer was going on, they offered me a whole year extension. They offered me. So ironically, I was a faculty member at Yale before I was a student there, because my position was, the title was assistant instructor. So that's the lowest of the low, right? There's professors, the assistant professors are the lowest, then they're the instructor, well, then they're lecturers, then they're instructors, and assistant instructors even lower. But technically, it was a faculty rank. I remember at one point going to get an ID card or something at an administrative office and being treated in a kind of offhand fashion. I didn't realize my rank was a faculty rank. And then suddenly the person who was working this looked it up and realized I was a faculty member. And all of a sudden she became much, much nicer to me.
Humble beginnings.
Which was nice in some respects, although in other respects it made me think, that you should be pleasant and nice to everyone, not
Yeah.
just people who are faculty members.
Yeah.
But anyway, so yeah, I was basically a full-time teaching assistant. It meant I had 2.5 TA positions. A normal TA position was 2 afternoons a week. I had 5.
Mm.
But what that meant, ironically, is I got 2.5 TA stipends, which meant that actually it was a pretty decent salary. And
Yeah.
in some ways, that's the best job I ever had. Was this job as a full-time teaching assistant for a year
Yeah.
at Yale. But during the time I was there, I mean, being a full-time teaching assistant, it probably didn't take me more than about 35 hours a week of work,
Yeah.
um, even putting everything together. And so I felt like I had some extra time, and I always liked computers. Uh, and so one of the things I did, so the person who ran the entire organic laboratory program, she had a system, like some student had made a program on her calculator that allowed her to do the scaling of grades, because there were probably 10, 15 different TAs grading different sections, and
Hmm.
some were just harder graders than others, and one needed to balance that out. Basically set the medians to be the same by well, it would mean adjusting down the scores of the easy graders, basically, and adjusting up the scores of the hard graders. And then also some people had a wider dispersion of grades, other people had a smaller dispersion of grades. And so you also set the standard deviations the same. But anyway, I thought, this is still a lot of work for her. And so I instead wrote a Fortran computer program to handle the whole thing and make a nice table at the end that had all the grades and the scores and so on and so forth. So that was sort of my first project. And maybe that's some, no, I was, no, this is how it worked. So I did that, but then I also attended, they had sort of some evening talks by the different faculty members in the department,
Mm.
just giving a little bit of an overview of the kind of research they did. And I went to those too. And I was particularly intrigued by the one by Ken Weiberg, who ended up being my PhD advisor. And so in the second semester, I actually began doing, I think it was already then, I started, or maybe it was only the summer, I started doing research in his lab, and then eventually enrolled as a graduate student and began, the graduate program over again at Yale. But also I sort of did this backwards in the sense that I joined the research group before I became a graduate student.
It's quite an unorthodox journey there.
Yes, indeed.
What? So, what was it about the research that was going on there that particularly interested you?
So I think what particularly, well, two things. One is it was computational, and as I said, or at
Mm.
least had a large computational component. And as I indicated before, I'd always liked working with numbers and with computers, and I liked computer programming, and so that appealed to me. But I think the other thing that appealed to me is that the way he sort of presented what he was working on was from the perspective of, this is an interesting phenomenon, and I really don't understand it, and I want to understand it. And most of the
Mm.
other people were sort of in a way, in a more goal-directed, more practical goal-directed formulation.
Yeah.
His was sort of more explicitly curiosity-driven. And I think the other thing that appealed to me is it was curiosity about some pretty basic, pretty fundamental principles, and about some things that I had wondered about myself. I don't remember exactly all of these, what they were at the moment.
Sure.
But it might have had to do something with why IR frequencies in different carbonyl compounds vary the way they do, because that's something that I'd always wondered about.
Mm.
I felt that the traditional explanations in textbooks didn't quite hold water. Whatever it was something like that, where he was saying, this is a phenomenon, it's well known, this is the traditional explanation, but it doesn't really hold water if you look closely. And so we're trying to figure out what's really going on here. And that appealed to me.
Yeah. So, as you're over your graduate school time, what was kind of like, what were you working on as a student?
So I worked on a whole variety of projects, actually. My thesis title was something like Studies of Resonance in Organic Chemistry, because that was sort of the theme that I could think of that linked the various, at least most of the various things that I worked on.
Mm.
But I really worked on a series of different projects about small molecules. And as the name of the thesis suggests, a lot of them were about conjugation. So one of my first projects was looking at butadiene and butadienes, where you substituted one or more of the carbons in the butadiene structure with nitrogen or oxygen. And in particular, we were looking at the degree of conjugation in those systems, and what the rotational potential energy profiles were, and how we could understand that in terms of the molecular orbital interactions, basically. We also
The rotation, I don't follow that part then.
so think about 1,3-butadiene.
Okay.
It basically wants to be planar, right? Because that's how it's conjugated.
Mm-hmm.
And it can be either sort of in a zigzag form with a trans conformation around the single bond in the middle. That's called the S-trans conformation.
Okay.
It also can be cis around that single bond in the middle. That's called the S-cis conformation. Although it turns out that's a maximum. It's not a it's a maximum, and that the other minimum is twisted a little bit. So it's called a gauche structure.
I see. Okay.
And then when everything is rotated 90 degrees, the energy is pretty much at a maximum because you've lost the conjugation. But those profiles change depending, if you have, as I said, nitrogens and oxygens in various positions.
I see.
And there are various considerations that go into that, and that's what we did, was to look at what the different component contributions were. Things like the traditional resonance interaction of the double bonds, also electrostatic interactions. For instance, if there are oxygens on the end, they're negatively charged, they repel each other. There are steric interactions. That's what's happened in the S-cis butadiene. And also, for instance, if you have a nitrogen in one of the middle positions, the lone pair is capable of conjugation as well, not just the pi bond. And so those are all considerations that need to be taken into account.
Some question. I actually have a question kind of about that, because something that, so when we talk about conjugation, it's like, I guess when you first learn it, obviously it's much more like it either is conjugated or it's not conjugated, basically. But you said like degree of conjugation. So I guess what I'm wondering is like, can you put units on it? And like, let's say, what is, at the end of the day, like, what is the significance of conjugation? Like, what is that?
I guess to me, I would say that the measure really is the energy associated with it, the stabilization energy.
Okay.
So I would say how much is the energy of the system lower than it would be absent the conjugation.
I see. Okay, that's a good way of putting it.
That's, I think, how I would quantify it, and I think a lot of people would agree that's a reasonable way to quantify it.
Okay.
The tricky thing is, how do you define the system that doesn't have conjugation, right? That's the hard part.
Is that personal opinion? The unsaturation version?
Yeah, there's no way to really cleanly define the corresponding system without conjugation. There are various ways you can try to do it that are reasonable, but they all have their limitations and imperfections. And so you can come up with different ways. So for instance, the rotational barrier is one way of trying to address that, because they say, okay, when you rotate 90 degrees, the conjugation is gone. And so the difference in energy between the rotated structure and the planar structure is a measure of the conjugation. But of course, the loss of conjugation is not the only thing that's going on when you do the rotation. There are also the steric interactions. There are also potentially electrostatic interactions. And even in the rotated form, perhaps there's some hyperconjugation going on that's absent in the planar form. So it gets to be kind of complicated.
Yeah,
and
it
different
does.
people have different preferred ways of doing this and end up often with somewhat different answers. But nonetheless, I'd say that there's a fair amount of consistency. And so, for instance, the conjugation in 1,3-butadiene, I think, 3, 4, 5 kilocalories per mole, I think almost everybody would agree that's about what it is, because the different ways of estimating it mostly come out in that range.
What level of theory were you using at a time? Were you using like perturbation theory, or were you using like DFT type?
So in terms of computational methods at that time, density functional theory didn't exist, or at least it didn't exist. It probably already, I think it really existed in like material science and such, but it was not generally used in chemistry. And things were largely done at the Hartree-Fock level.
Okay.
So the calculations I did always started with Hartree-Fock, and then, like you said, perturbation. Usually, we would also run some calculations at, say, MP2 or even MP3. Actually, we also did MP3 single point calculations. Subsequently, I think it's become quite clear that the odd numbered MPs are a little bit unreliable, so that probably in retrospect is not the best choice. But
to redact your thesis.
But yeah, no, we started with Hartree-Fock, then did MP2 and then did MP3 single point calculations. And I'm trying to think, I think even the MP2 calculations were single point. I don't think we optimized. I think at that time, it was actually very difficult to do MP2 optimizations. I don't think they had the second derivatives done analytically yet.
I'm just trying to think, because we do some EDA analysis schemes now, and it can get pretty, you can get pretty detailed how much information you want to pull from like different systems. So I'm just wondering like what what was available, I guess. That's
You mean in terms of what, analyzing the wave function? And
yeah,
such?
yeah. Well, that, and also like what sort of like you mentioned, like electrostatics and steric contributions,
Yeah, right.
conjugation, like how much information could you pull from
Right.
from those methods?
We did a fair amount with atomic charges. So we didn't use Mulliken. At the time, we mostly used a procedure called AIM. That's atoms and molecules, devised by Richard, I think it's Richard Bader, at McMaster University. So that was one of the ways we tried to address things. A lot of what we did was to try to just make different molecules that would illustrate the different principles. For instance, saying that if you have, again, one of these butadienes with oxygens on the end, that would be glyoxal, that ought to have electrostatic repulsion, whereas if you have, methylenes, you wouldn't have electrostatic repulsion, for instance. And so, to a large extent, we just sort of tried to make sense of the patterns of what different molecules did. But as I said, we also used atomic charges. We also, another thing, this is one of the things that I spent actually quite a bit of time on, was looking at the actual electron density distributions. And for instance, the extent of conjugation, one of the things we did was to look at the amount of charge density, the amount and distribution of charge density in a plane that bisected the single bond in the middle of the compound. And so we could, to some extent, say, well, if there's more conjugation, there ought to be more pi electron density. I was saying that we actually, I wrote computer programs to look at the wave function and quantify the electron density, particularly the pi electron density, in a plane bisecting the nominally single bond in these conjugated systems, as a way to independently quantify the extent of conjugation. So that was not in terms of energy, but in terms of electron density.
I see. That's really talking about this like fundamental, let's say like energy in these molecules is something that I'm pretty interested in. And I didn't even know like computational chemistry was even like a thing until I got to graduate school.
Mm-hmm.
And luckily, thank God we have a computational expert like in our group, and he's been very good at kind of explaining all these things. Otherwise, like, I've got to learn all this stuff on my own. But so moving then from, because I do want to talk about the research you kind of do now, because it's really cool, I think, more computational work. But just real quickly, kind of wrapping up with Yale, and then I think you did a postdoc there actually too. So I just assumed you kind of did more. I assume you did more or less the same, like just more computational work.
Not quite. Actually, I did a postdoc with Bill Jorgensen, who does computational work, but a different kind of computational work. He does these he does some quantum mechanical stuff too, but I'd say his biggest area is these simulations where you have lots and lots, say, of solvent molecules, as well as the solute molecule or the protein or whatever. He's subsequently, I think, very much gone off into the direction of macromolecules. But earlier, he spent a lot of time looking also at smaller organic molecules, and that's what I was involved with. So I did a short postdoc with him. I'd also looked at a few other people who did similar sorts of work. I decided I wanted to do a postdoc in computational chemistry, but a different kind of computation to broaden my background. And so so these are basically classical simulations, because they're much too big to treat quantum mechanically. And so you have to have what are called potential functions. That is, you have to have a mathematical model for how the molecules interact. And basically, it's a combination of electrostatic interactions that you model with atomic charges, and van der Waals type interactions that you typically model with a Leonard-Jones potential or something similar. That is something that becomes repulsive when you're very close, is mildly attractive when you're not quite as close, and then quickly becomes zero as you get further away.
Mm.
But those that's not always enough, because after all, molecules can become more polar in a polar environment. So for instance, the water molecule, in the gas phase by itself is less polarized than it is when it is in water, because in water there's a medium around to stabilize charge separation so it's beneficial for the water molecule to become more polar in that
Mm.
environment. All right. Now, the potential functions that are developed generally take that into account. That is, they're developed to match experimental data in terms of the properties of a liquid. So the charges that are used for these simulations for water already take into account the polarization that happens in an aqueous solution. But nonetheless, there are situations where that sort of averaged approach may not be enough, and to accurately model what's going on, you might need to have charges that are adjustable. That is, charges that can become more greater or lesser depending on the local polarity of the environment. And so what I worked on for the 9 months I was in this postdoc was the possibility of using polarizable potential functions like this in some of the simulations to see how that would work and if it might improve agreement with experiment in some cases.
That sounds computationally expensive, but
it is. It is sometimes done, but I think one of the things that we discovered in all of this is, these simulations, one way of doing them is what's called molecular dynamics, where you literally simulate over time what happens using like Newton's laws of motion. The other approach is what the Jorgensen group mostly did, was Monte Carlo simulation, which is a somewhat different approach that is in some ways more efficient computationally. Certainly each Monte Carlo step is much, much less expensive than each molecular dynamics step, because in the Monte Carlo simulation, you just move one molecule and then recompute things. And so a lot of stuff stays the same. Whereas in a molecular dynamics simulation, each time step, everything moves. So each step is much, much more expensive for molecular dynamics. Now in Monte Carlo, you need to have more steps, but nonetheless, the steps are so much cheaper that it usually ends up being beneficial in the end anyway. But one of the things that we discovered in the process of doing this is the trouble is with polarizable potential functions, even if you move just one molecule, now everything changes. With non-polarizable potential functions, if you move just one molecule, the interactions between that molecule and all the other functions.
Yep.
So, so with these Monte Carlo simulations, if you move just one molecule and you have normal potential functions, you have to recalculate the interaction of this molecule with everything else, but the interactions between the other molecules remain the same because they didn't move. But if they're polarizable functions, then even if just this molecule moves, it can change the polarization on these molecules and therefore changes their interaction energy as well. So what happens is suddenly a Monte Carlo step takes about as much time to calculate as a molecular dynamics step. And so it makes the time advantage of Monte Carlo over molecular dynamics largely evaporate. I mean, you can set a cutoff and say, well, once you get far enough from the moved molecule, then of course the interactions aren't going to change. But nonetheless, I think the net conclusion, at least that I came to, is that for Monte Carlo simulation, these polarizable potential functions were really not practical, even though for molecular dynamics simulations, even though they were expensive, they could be practical in situations where they improve the results.
That's really that's really
But,
cool
but,
stuff.
but anyway, and so that was my postdoc. And just to finish that thought, I'll say that I ended up leaving the postdoc early, not because there was anything wrong with the postdoc. It was a good postdoc. But as we discussed before, my career intention all along was to find a position at a good quality small undergraduate college. And there are not many such schools or positions. And so I already started applying in my first year. And when an offer came through, I just figured, look, if I don't take this position now, I may never again have the opportunity to get something comparably good,
Hmm.
and so I better take it. And so even though I would have preferred to stay in the postdoc for another year, or even 2 years, it was a good postdoc, but
You can't
I
pass
felt I
up.
couldn't afford to give up the opportunity that came my way at
Yeah,
that point in time.
yeah, it's really definitely don't want to give up. A position at a small university teaching undergrads sounds very, especially to me, it sounds very appealing. So I definitely hear you there. Um, so I guess kind of moving into now your Swarthmore career.
Uh-huh.
I know you were kind of. Do you have any graduate students, or is it really just kind
No,
of undergrads?
strictly
Yeah,
undergraduate.
yeah. The first actually question I wanted to ask is you know, working with undergraduates, like what's kind of been the like some of the most rewarding aspects of it, right? Because I mean, at the end of I guess it's more like fundamental understandings, right, of like the chemistry you're doing. But what's kind of definitely been the most rewarding, you think?
So so what, like, most rewarding about the research, or so
Research.
the truth is, a lot of the research I've done, the majority of the research I've done as a faculty member, I really have done solo. So
Okay.
I've had undergraduates work with me on a few projects at various times, including this most recent one that you seem to have an interest in, about electrophilic aromatic substitution.
Yep.
But a lot of the research I've actually done uh, either solo, or I also have done a lot of collaborations with people at other schools.
Okay.
That is, it's happened quite a few times in my career that somebody, particularly who's an experimentalist someplace else, wants to collaborate with a computationalist and approaches me and asks if I'd be interested in doing the computational part of some study. And I'm often game for that. And so that's what a lot of my research has been in the end. Um, I have to say, I've not found it easy involving undergraduates in research. It's in a way harder than I anticipated.
Mm.
Um,
I mean, I
in
can't
some
imagine.
ways, I think.
I can't
Sorry.
imagine. Like I was gonna say, I can't imagine like learning computational chemistry like without really having like PChem or like like or
Well,
even
that's one of the issues. Is so I think that it's hard for me to involve students until they've had a significant amount of chemistry. Some organic. They need to have a fair amount of organic, preferably a whole year of organic. But also, it really is useful to have some physical chemistry. Although, interestingly, I'd say it's not necessarily even the quantum that they need. But for what we do with the computations is we're usually doing things with energies or and structures. That's usually what we're using.
yeah.
And knowing what to do with the energies in some sense requires having a reasonable understanding of physical chemistry. So you're
Mm.
right. One of the things is it's, I think, more difficult for me than for some of my colleagues to use students who are earlier on in the curriculum. Um, and I guess the other thing I'd say is one of the things that's allowed me to do a lot of research on my own is computational chemistry. In some technical sense, you could say is easy, right? That is, to actually run the calculation, I need to have computer hardware and such, but actually running the calculation is in some ways a fairly easy process compared to, say, doing an experiment in the lab.
Yeah.
So that means I can do quite a bit myself. But the flip side of that I hadn't really thought about before becoming a professor, is a higher proportion of the work is involved really, thinking deeply about what you're doing and why you're doing it and what you should do next, as opposed to the actual doing. And that thinking is often hard for an undergraduate to do.
Mm.
You need more experience and deeper knowledge to do that well. And my observation is that the people who've made the best use of undergraduate researchers are often in areas where there's quite a lot of physical work to be done in the lab, often using a technique that, it takes a little while to learn, but once you've learned the technique, okay, now there's a whole bunch of experiments that just need to be run, and the students can run those experiments and, gain a lot from doing them. And yes, they're also, helping to analyze the results, but in some sense, they're uh, that's an amount of physical work that it would be difficult for a single person like a faculty member to actually get through by themselves. And so they really kind of need undergraduates to help do this. But with calculations, the flip side is I sometimes have found it hard to keep the students occupied because, okay, you set up the calculation, but now what do you do while you're waiting for it to run? For me as a professor, it's not a problem because I've always got other stuff to do.
Right.
And also, even with the research, there's thinking about what needs to be done, working out the results, so on and so forth. But a lot of that work, the students aren't far enough along to be able to really help with that terribly much. And so, I've often found it a little bit tricky. Involving the students works the best if I can make a really rather concrete project that involves running a series of similar calculations on a bunch of different structures. And in those cases, I have sometimes been able to involve students.
This is something I've discussed with our computational expert in the group. We talked about this before, but like, do you think I think it'd be pretty cool if like some universities offered like a computational like class, like computational chemistry class. Like, I don't know if you've thought about this, or like, I don't even know if you have one. Perhaps maybe you already have one, but like, do you think it'd be possible to do that? And do you think there'd be enough interest from
I'm
most
sure
universities?
This could be possible, and certainly plenty of schools have a computational chemistry course.
Yeah.
We don't have one here. So, being a small department and undergraduate only, there's only so much we can offer, and not only in the sense of faculty resource, but also only so much that students have room for in their schedule.
Yeah,
so one
enough.
of the things is our chemistry major, once you've covered all the requirements, there's not much room for electives, especially in the sense that students also have, it's a liberal arts college. Students have distribution requirements and such. They also have other interests.
Yeah.
And so usually students are going to take the courses they need for the major and not much chemistry beyond what's required for the major. And so what that means is that a typical chemistry major has maybe one or two electives in their time here, sort of our upper level seminars, as we call them.
Mm-hmm.
And so at any given year, we generally can only offer about 3 of those, typically, both because we only have so many faculty, but also because there are only so many students. And if we offered more than about 3, the class sizes would become actually unhealthily small. So that's all to say that the one seminar that I offer is typically physical organic chemistry, which is a bit broader than computational chemistry, and that's intentionally so. And when I've taught it, I have sometimes been able to put some computational chemistry in it. Not a whole lot, but at least a little bit.
Yeah.
Sometimes we'd have students learn how to run some calculations and do them as part of some of the homework assignments. But anyway, the answer is sure, I've thought about a computational chemistry course, but I've always come to the conclusion that it's more important to have a physical organic chemistry course than a computational chemistry course, and we really don't have room for both.
That's fair enough. All right, so in a perfect world, you could teach the computational course.
I mean,
what are some?
I would have to do some additional work in preparation to teach something that's broader than just my very particular area of computational chemistry. But
what are some of even people that are listening? What are some the high level things people should know, kind of like going into it? Let's say you've taken let's just take hypothetical students who's taken organic and PChem. They want to next learn computational chemistry. What is some of the high level things that they should learn?
Yeah.
And what are a couple of tips and tricks you'd recommend students to help them along?
So I haven't put together a syllabus, but
of course. But
okay, so the first thing I'd say is there are some good books out there, like by Chris Kramer, that are overviews of computational chemistry. I forget what his is called. I have it somewhere up on my bookshelf. It may even be called just computational chemistry. And so that's a good place to start. But I think one of the first things I'd want to do, or one of the main things I'd want to do, is introduce students to the different kinds of computational chemistry and what they're good for and how they work. So the kind of computational chemistry I do, ever since I've been a faculty member and when I was a graduate student, is electronic structure calculation, right?
Yeah.
But that's only one kind. There are also these simulations that I talked about, for instance, Monte Carlo and molecular dynamic simulations. That's a whole other area of computational chemistry, so I want students to know something about those areas too. Then there's the sort of even more, in a way, simple kinds of computational work done in the pharmaceutical industry, where they do docking studies, for instance, basically seeing how does this molecule fit into some other molecule. But that's very important in the pharmaceutical industry.
Sure.
And they do these things called CUMFA. That's, I think, comparative molecular field analysis, where they sort of try to develop a combined electrostatic and steric field, you might say, and line it up with the field of potential molecules that might bind. So that's something I'd want them to know about. So I think that would be my goal with a computational chemistry course, would be to introduce students to the fundamentally different kinds of computational chemistry. What the math, what the physics and the assumptions underlying them are, what kinds of things they can accomplish and what they can't accomplish. And then probably, since electronic structure calculation is what I know best, I'd go in a little more detail into electronic structure calculations, talking about a little bit about the different correlation methods, certainly talking about what basis sets are and how they work, and the kinds of properties you can calculate. So obviously there's energy, that's really important. There are also the vibrational frequencies, which give you thermodynamic corrections. They also can give you IR spectra. You can calculate vibrational circular dichroism spectra. You can predict things about ultraviolet visible spectra from looking at, like the HOMO-LUMO gap. NMR properties, both coupling constants and chemical shifts. That's an important thing to be able to calculate. Also just structures, conformational searching, and that's another thing that's important. And I skipped over molecular mechanics. That's a whole other area, molecular mechanics.
Yeah.
Which can be very useful for conformational searching for sure. And conformational search methods are also in and of themselves an interesting area, because more complicated molecules can have enormous numbers of conformations, and how do you find the lowest energy ones?
Mm-hmm.
Systematic search ends up being impractical when you get beyond a certain size, and so there are stochastic methods that you can use, and those are important to know about too. So
there's a lot to be done with it, but it's really an exciting field, because I mean, like I said before, like I didn't even know it was a field until I got to graduate school, and I've been pleasantly, I think a great way to put it is pleasantly surprised with it.
And I'll also say it's developed a lot. I mean, I remember when I first went to graduate school and I was warned by some people, oh, you shouldn't go into computational chemistry because nobody believes that stuff. But it's, of course, grown into a very important area. And, of course, it is true that you can't just take what comes out of a computation as the truth, right?
Yeah.
Computational methods are all approximate at some level and have limitations. But nonetheless, computational chemistry has proven to be very, very useful and to be accurately predictive for a lot of things. And it's grown enormously, partly because computer power has grown. I mean, that's a lot of it. Computer power has grown, but also just the methodology has developed a great deal.
Something I kind of want to pick your brain about a little bit here is the I make a joke. It's like you can't get JAX without a computational study, where it's like literally it seems like nowadays every paper has got a computational study. And my gripe with that is that like most of the time it's just there for being there. It's not like there's not
a reason for it.
There's not particularly anything you didn't already know about it.
Yeah.
I don't know why the perspective of that shifted to be that way. Computational chemistry can ask great questions, but it doesn't like.
Right.
I don't know.
I think that's a fair gripe. No, in fact, I have a similar gripe that I often bring up when I do. Okay, so I've never taught a computational chemistry course, but as I said, I've taught a little bit of computational chemistry in my physical organic seminar. Mm-hmm. And when I've had research students, I often take a few days to give them kind of a primer in computational chemistry. And exactly one of the things that I always say is there's a tendency for people to say, oh, I'm interested in studying this molecule. Let's calculate it. Right? And it's like, well, but why?
Yeah.
What are you going to get from this calculation? And there's often sort of this sense that, oh, if you're interested in a molecule, you should just calculate it. But it's sort of like saying, well, gee, this is a molecule I'm interested in. I want to run an experiment on it. Oh, well, what experiment and what information are you hoping to get from that experiment? Because calculation, I like to tell people, there's theory and there's computation. So theory is really sort of thinking very fundamentally about how things work and how to model them. But
Yeah.
computation I see is distinct from theory. I see computation as using models that have been developed to answer chemical questions, really. And so in that sense, it's a really, you should think about it much the same way you do about an experiment. So with a calculation, think, what is the question you're trying to answer? What is the property you're going to calculate that is going to tell you something that you don't already know, like you said? So maybe you want to know something about the structure of the molecule. If what you want to know is what is the low energy conformation, okay, that's a concrete question. Calculate, think about what the different possible conformations are, calculate them, figure out what's the lowest in energy. And of course, you always have to consider, is the calculation right or not? But even assuming the calculation is right, what is the property that you're trying to predict?
Yeah.
And what's it going to tell you? So it could be, as I said, that it could be the NMR spectrum. I mean, maybe you're trying to figure out if some structure is this or that, and you could calculate the NMR structure for both and see which one fits the experimental data. Okay, that's a well-defined question. For the mechanism of a reaction, you can't calculate the mechanism, you have to have hypotheses. But if you have more than one hypothesis for a mechanism, okay, you can try to calculate the different routes and see which one is lower in energy, or if even both exist.
Yeah.
If there's an intermediate that you're postulating, yeah, you can see if the intermediate exists, what its structure looks like, how high its energy is. Those are all concrete things to do. But I agree with you that there's a tendency often among people who are, especially people who are experimentalists, who are interested in doing some calculation, to sometimes just sort of say, let's calculate a molecule or calculate something without thinking about what it is they're really trying to get from the calculation.
Yeah, especially in my world, it's always like the reaction coordinate diagram. Like, what's the barrier of this? And it's just like, I don't know. It's just like, it's all this. I don't know.
Although that would argue is really valuable,
and that is important. Yeah.
Right, because for instance, if there's some reaction you're looking at and you think you know the mechanism, then it makes a lot of sense to calculate the intermediates, the barriers. Because for instance, if what you find is the barrier, let's say you find the barrier is 35 kilocalories per mole for a reaction that goes smoothly at room temperature. Well, something's wrong because that barrier is too high to be able to cross it at room temperature. So unless your calculation is way off, it means you've got the wrong mechanism. There's something more complicated going on. On the other hand, if it fits, well, maybe it doesn't tell you in some sense anything more than you didn't already at least think you know, but at least it's something that could have disconfirmed the mechanism that didn't. And so that's in some sense evidence in favor of the mechanism.
Yeah. So some other questions I wanted, because originally I actually wanted to bring on, because I wanted to talk about the electronic factors for like the ortho and para substituted electrophilic aromatic substitution reactions. And the reason why I was originally interested in this is because I gave my second year seminar on meta-selective CH functionalization techniques. And in like my introductory area, I briefly discussed that if you do, if you have, electron-rich groups, you're going to get basically ortho-para selectivity. I mean, in those types of reactions. And I arbitrarily showed that you would get like a 50-50 mixture of the ortho and para products for those types of reactions. What I kind of put it there because the point was you don't get, if you have a donor group, you don't get meta selectivity. That was the point. I didn't like statistically analyze like the ortho and para. But then of course, what it's on your slides, you're required to know. So I got asked, is it really like a 50-50 mixture? And I was like, no, it's definitely much more complicated than that. And, I guess you can kind of answer those questions a little bit. So, if you're doing, well, what are the electronic factors that go into, the ortho and para products of electrophilic aromatic substitution reactions?
Right. So yeah, I'd say, by the way, to begin with, I'd say that a long time ago, we used to do an experiment for an advanced lab class here where students actually carried out bromination of different substituted aromatics.
Safe.
And we analyzed the product distributions by, I think it was GC, although possibly we used NMR as well. And I can say experimentally, one of the things I remember is that for the stronger electron donors, there was a strong predominance of para substitution over ortho substitution.
Hmm.
So empirically, it's something that I've been sort of aware of for a long time. So I don't know, is there a way that I can share a screen while we're doing this?
I think so. On the bottom, it should say share.
Okay, because, all right, let me see if I can do something, because it's going to be hard to explain this, I think, without pictures.
People love pictures.
So let me see what I can.
Yeah, along the bottom of the.
Yeah, no, I can see.
There it is. Yep.
All right. So this is actually a talk that I was putting together for that. By the way, that's Ariana. Yeah, she's the student who worked with me on this. And so this is a talk about this topic, but I'll jump ahead to the interactions that you were asking about. So this is just showing some results. Okay, so let me jump ahead to the
good old Hammett parameters.
Yeah. Okay, so in terms of the interactions that I think are involved here, one thing you can see, can you see my cursor?
No, I don't think so.
All right. Oh, well. I wonder if... Can you see that laser?
Yep.
You can see that?
Yep.
Okay, excellent. So, so this is one way of thinking about it, that when you have a substituent para, the conjugation sort of looks like this. Whereas if a substituent is ortho, the conjugation looks like this. And you can see that that para arrangement as a triene is more stable than the ortho arrangement. So that's maybe one way of thinking about what's going on. But the other is to think about molecular orbital interactions. So here are the molecular orbitals for the cyclohexadienyl cation. There's the lowest energy orbital. Here now is the second one, which is the highest occupied one, since we have a cation. There's the lowest unoccupied. And then if you think about a substituent that has a pi system, it's going to have a pi orbital and a pi star. At least that's the simplest way of thinking about it. And now what are the kinds of... Oh, and it's easier to think in subsequent slides about these MOs by taking a top view. So here on the left and now on the right, you can see top views of these same orbitals. So what are the interactions? So pi2, that's the HOMO of the cyclic cationic system, has no interaction with this pi orbital because there's a node here on that middle atom. And likewise, there's no interaction here. On the other hand, with pi3, that's the unoccupied orbital of the cation, you can see there is interaction here and here. If a substituent is ortho, you can see that there's now an interaction both with pi2 and also with pi3. And so that's going to be important in the following slides. Okay, so by symmetry, as I said, those two are out. That one's an interaction between two empty orbitals, so it doesn't matter. That's also an interaction between two empty orbitals, so it doesn't matter. What we're left with are that interaction potentially as being important, and that one, and those are both favorable interactions. And then that's a favorable interaction, and this is an unfavorable interaction. And the long and short of it, I'll show this again in subsequent slides, is first of all, that this pi3 has a bigger lobe on this middle atom than the outer lobes. That is, at the simplest Huckel theory, those lobes are the same size. But if you do a somewhat more sophisticated calculation, this paralobe is bigger than the ortho lobes. And so this favorable interaction is probably somewhat stronger than this one. And that's an interaction that results from the substituent being a pi donor. And so that I think is probably the main reason, actually, why para substitution is preferred over ortho substitution with stronger electron donors. Although another thing that might be going on, you can see over here, which is that if the pi donor is quite strong, then this pi orbital here is quite high in energy and can have a repulsive interaction with the filled pi2 orbital of the aromatic, well, no longer aromatic, but the cyclic system, whereas that unfavorable interaction is absent when the substituent is para because of symmetry. That is because there's a node right there in the cyclohexadienyl system orbital.
Mm.
Okay, so here I again have the diagrams to show what's going on. So if we have in the para position an electron donor, we have this favorable interaction. And again, it's more favorable to the para position than the ortho positions because this lobe is bigger. And we don't have a repulsive interaction between this and this because there's a node here. If that same electron donating group is ortho, you still have a favorable interaction between this and now you can see I've twisted the aromatic system, so we're still interacting with here.
Mm-hmm.
So from here to here, that still is a favorable interaction. I haven't shown it just so the diagram doesn't get cluttered. But now you potentially have this repulsive interaction, which was absent when the substituent was para because of the node at this position.
Oh.
So those are my justifications for why the more strongly electron donating a substituent is, the more there's preference for para over ortho. It is both because the favorable interaction is stronger and because in the ortho position there's potentially an unfavorable filled interaction.
Oh, that makes sense. Okay.
On the other hand, if you have an electron withdrawing group that is para versus ortho, even though electron drawing would generally give you meta substitution, that would be the normal expectation. What I've done now is to lower the pi and pi star, because for an electron withdrawing group, those should be much lower in energy. For an electron donating group, they'd be higher in energy, as I drew on the left-handed the diagrams on the left. Okay, so now we have an electron withdrawing group and potentially in the para position. Well, now the argument is the energy gap from pi to pi 3 is big enough that this is probably not an important interaction. These are close enough in energy that could be an important interaction, as in fact it is over here on the left. But because of symmetry, there's no interaction here. But, and likewise, by the way, there's no interaction here. All right? There's no interaction between pi 2 and pi star, again, because of symmetry. But if we have the pi 2 orbital, if we have the substituent ortho, now the interaction is from here to here. And so the argument is, I think I misstated that a little bit before. These are somewhat close in energy, but the assumption is that these are even closer in energy. The pi of the occupied pi to the pi star of the electron withdrawing group, which would be low-lying if it's an electron withdrawing group. And so now potentially you actually have a favorable interaction that involves donation of electron density from the cyclic system to the electron withdrawing substituent. But that's only possible in the ortho position. It's not possible in the para position because of the node at this position. So that would be my argument for why, if you have a strongly electron withdrawing group, there might actually be a preference for ortho substitution over para substitution, even though meta is sort of what you expect overall. And in fact, what the calculations show, this is just a figure from the paper,
Mm-hmm.
is that the overall fraction of ortho can be more than the statistical amount for some electron withdrawing groups. I would tend to say electron withdrawing groups that are enough electron withdrawing to lead to this preference for, say, ortho over para, but not so electron withdrawing as to make meta the predominant product. And in fact, experimentally, this is what I've showed in some of the, not only experimentally, but computationally. We go back here. Here you can see both computational and experimental results for electrophilic aromatic substitution on 3 aromatics with an electron withdrawing group, a pi electron withdrawing group. And what you can see is not only computationally, but also experimentally, there's a substantial amount of ortho.
Yeah.
Not so much in the case of nitro. Well, actually, it depends. This case, yes. But certainly, for instance, in this with the cyano case, even experimentally, there's more than the amount of ortho is more than half as much as the amount of meta. So in some ways, it seems to me that these substituents you might almost say they're not so much meta directors as they are ortho meta directors, because these ratios between ortho and meta are comparable to the ratios of ortho to para or para to ortho with the classic ortho para directing substituents. So anyway, that's I think one of the the primary interesting outcome. Let me stop sharing here. How do I do this? How do I? Yes. There we go. Okay.
There you go.
That's, I think, one of the primary interesting outcomes from the study. And it was even there in the experimental data. I just, I hadn't paid attention to it earlier, because these substituents are always portrayed as cleanly, pretty cleanly meta-directing in textbooks. But if you look at it, some of them really give, as I said, comparable amounts, not quite as much perhaps, but comparable amounts of ortho to meta.
Yeah, I mean,
see that experimentally and in the calculations.
I know. Generally speaking, the meta electrophilic aromatic substitution reaction can be pretty messy. That can be quite not fun reactions to do. Put it nicely, but no, that's really cool because, I mean, that is, because electrophilic aromatic substitution has been. I mean, it's got to be one of the earliest reactions ever. I think probably right. It's one of the cornerstones.
Pretty early one, yeah.
It's one of the cornerstones of chemical synthesis, and
yeah, absolutely, you're right.
I think that level of understanding has kind of been. It's only been experimentally. I don't know if anyone's actually seen it computationally, what is actually happening there. It's really cool to see. I know I could be wrong on that. I'm really familiar, but nonetheless, that's still really cool, especially for, we typically think when you have electron withdrawing groups on and to do electrophilic aromatic substitution, the general consensus is, or at least when you teach at an undergraduate level, it's you just get meta selectivity and that's it. But as we just saw, depending on the electron withdrawing group, it's certainly much more nuanced than that.
Right. Right. And one of the, just to add to that a little bit, if one just had seen it experimentally, I think you might say, oh, and, it may be some sort of complex mechanistic effect. Maybe it's some pi complex. Maybe it's somehow the incoming electrophile interacting with the substituent and being directed by the substituent. There are various mechanisms you can imagine. But the fact that you can reproduce this just with a very simplified model of the cation.
Yeah.
And nothing else around, not the transition state even leading to it, suggests that you don't need to invoke complex interactions like that to explain the tendency to get a fair amount of ortho. It's sort of pretty fundamental to the nature of the intermediate.
Yeah, that's really fascinating. Really, really cool stuff. Some other as we kind of wrap up here, one other thing I wanted to pick your brain about is your protocols for Hammett substituent constants, right? So this can be a little bit. This might be a little complicated. I don't know, but just kind of your general thoughts on how to approach the Hammett substituent constants and kind of what you've taken away from your time with that.
Well, I mean, as I'm sure they're in a way to quantify the electron donating, electron withdrawing character of different substituents, both inductively and by resonance, the different parameters. And so, one of the ways I tried to understand what was going on here, because in this project, you see, it really began with my thinking that cyano was an outlier, giving a significant amount of ortho product, or even at lower levels of theory, it's even predicted that the ortho is the main product. And but I tried all sorts of ideas for what might be causing it, and nothing worked, basically. And so eventually I started thinking, well, maybe this is a more general phenomenon. And so I decided, okay, I should see if in general the ortho para versus meta directing ability is that I predict by calculating the stability of the different substituted cations, does that correlate well with Hammett parameters, right? Because I thought maybe cyano was going to be an outlier, right? But if cyano is in the same line as the other parameters, then it suggests, no, it's nothing special about cyano. It's a more general sort of phenomenon. So that's sort of why I did that initially. But I found that I couldn't get all the parameters that I needed. So the classic sigma P and sigma M are available for a vast number of substituents experimentally, and presumably that's because it's pretty easy to measure. You just have to get some pKa's.
Yeah.
But the sigma plus, which is what I wanted, because that's particularly appropriate in this case, the sigma plus is much harder to measure because it's based on the rate of subolysis of a benzene with an ice. It's called a cumulochloride. Benzene with an isopropyl group and a chlorine on the benzylic position. And so that's a much, much harder experiment to run. And so understandably, sigma plus experimentally is only available for a limited number of substituents. And I wanted it for a wider variety of substituents. And I wanted it for electron withdrawing groups as well as electron donating groups. And so I thought, well, maybe I can calculate them, but I want to first see if I can calculate, ones that are well established properly. And so, yeah, I came up with a protocol for calculating these parameters that gives the absolute agreement is not high, but if you're willing to accept an empirical scaling factor, the correlation between the experimental values and the computed values is excellent. And so, provided you have enough points to make a good calibration curve, so to speak, I'd say that the calculated values, I think, are really quite reliable and are particularly helpful when the experimental values aren't available. Although also in the course of doing this, Ariana Yet, my student, and I, we discovered that some of the values that are reported in the literature are probably wrong because they really are clearly outliers.
Yeah.
And the ones that were, we could usually come up with a rationale when we looked closer at the experimental data for why they might be in error.
Yeah. Well, Professor Rablen, I want to thank you so much for your time and coming on today. It was a pleasure talking to you.
All right.
For the viewers out there, thank you again for listening to another episode, and I'll see you on the next one.
All right. Thank you.